Hi everyone, welcome to today's webinar. This webinar is being brought to you by the Resilient Power Project, which is a project of Clean Energy Group, as well as Misc, the Northeast Electrochemical Energy Storage Cluster. And our topic today is fuel cells for electric supply and grid support. And our host for this webinar will be Val Story. Val's a project director at Clean Energy Group. Before we get started with that, I would like to go over just a few quick housekeeping notes. So today all of our participants are in listen-only mode. This means that you can hear us, but we can't hear you. You have a couple of options for joining the audio portion of this webinar. You can use your telephone or your computer mic and speakers. And you can see some instructions for that on your screen. Another important note is to please submit your questions as you think of them throughout the webinar. You can do that by typing them into the question box on your webinar console and hitting send. We will be queuing all of your questions up and answering them during a Q&A at the end of the webinar as time allows. So again, please type your questions in as you think of them, and we will queue those up to answer at the end. A final note from me, this webinar is being recorded, and you will find a recording of this webinar as well as all of our previous webinars from the Resilient Power Project archived online on the web addresses that you see on your screen. And with that, I'm going to pass this over to Val Story.
Hi, everyone. Thanks for joining today's webinar. Sam, is there feedback?
No, it seemed to have gone away.
Oh, hear me?
Yep, I think you're fine.
Okay, great. Good. Sorry about that. All right, so apologies. Thank you and welcome to the webinar, everyone. As Sam mentioned, today's Resilient Power Project webinar is being brought to you by the Clean Energy Group and the Northeast Electrochemical Storage Cluster Project. Just some background before we go into the three main presentations that we have queued up. The webinar is hosted in part by Clean Energy Group, which is a national nonprofit that is working on clean energy finance policy and technology issues across the country. Our focus is on states and on communities, specifically through the Resilient Power Project, which is funded in part by JPB. We are trying to expand the markets for clean energy, renewable power, and scale up those markets. We also manage a sister organization called the Clean Energy States Alliance, which is an organization mainly of the major state energy policymakers across the nation who manage system benefit charge funds. We are funded by their membership and through several foundations. A couple of them you can see on your screen. Next slide, please. The Resilient Power Project is an effort to support the deployment of resilient power technologies, mainly through this project, solar and storage, focused on multifamily housing and affordable housing. It also includes technologies such as CHP, micro-CHP, fuel cells, and microgrids. And we do this by supporting state efforts to plan and implement resilient power programs. We work with municipalities, developers, and the national labs. We also offer technology support and technical services. We offer technical services through this Resilient Power Project. On our website, you'll find a couple of our recent reports, links, archives to our free monthly and weekly newsletters, and other information on upcoming and previous webinars. Next slide, please. The Misc, or Northeast Electrochemical Energy Storage Cluster, is a network of industry and government and non-government groups working together to help businesses scale up and provide energy storage solutions through the Northeast. The project is coordinated by FCAT, the Connecticut Center for Advanced Technologies, and today's website is brought to you in partnership with Misc. Next slide. Thank you. So we have three guest speakers today. They'll each be speaking for 10 to 12 minutes, and we will hold Q&A until the end of their presentations. I will present each speaker at the start of their presentations. The first speaker today is Andy Skok. He's the Senior Director from Fuel Cell Energy. He is Senior Sales and Marketing Executive for Fuel Cell Energy, which is in Danbury, Connecticut, where he has over 30 years of experience in many different management positions. His areas of focus have included R&D, first-of-a-kind demonstration projects, new product development, development of a world-class field service group, construction management, and more. He received his undergraduate degree in materials engineering from Wilkes University and attended Yale University's Chemical Engineering Graduate School. Andy, thank you for joining us.
Thank you, Bill, and good afternoon, everyone. Next slide, please. So I've set this up. What I'll do is I'll talk just very briefly in the beginning about who fuel cell energy is, for those of you who don't know, and then a little bit of the attributes of why someone might want a fuel cell, followed by 3 case studies that show the different ways fuel cells can be applied for electric supply and grid support. So a little bit about Fuel Cell Energy. We're an integrated fuel cell company, which means we basically take raw materials and manufacture them into the fuel cell. We've done the design work. We do service on the units. We are OEM manufacturer of fully packaged fuel cell power plants, and we also do project development, engineering, construction, and we've got over 300 megawatts of fuel cells installed and in backlog all around the world. Next slide, please. So why would someone want a fuel cell? The benefits of fuel cells, you can see over on the one side sort of a typical fuel cell size for us. We've got our small plants at 1.4. We also have some plants at 2.8, and we do larger projects that are 10 to 50 megawatts in size. And the benefits for fuel cells are that they're an ultra-clean, reliable source of power. So they're a continuous, secure baseload, are very complementary to intermittent types of technologies like wind and solar, because they're there when the wind doesn't blow and when the sun doesn't shine. And they avoid grid transmission grid issues where the grid is constrained for some reason or another. They are virtually non-polluting in forms of NOx, SOx, and particulate matter, very, very low CO2, which allows siting in congested urban areas, which is one of the real benefits of them. High electrical efficiency, 47 to 70% electrical efficiency, electric only, and up to 90% with CHP. So they're the most efficient generating device that you can put on your system, and that helps drives, the efficiency drives the economics of the fuel cells to make them cost competitive many places with the grid. And they're a good example of distributed generation. You can put the power where it's needed at the customer site. It enables smart grids and enhances critical infrastructure support for places like universities, hospitals, and other applications like that. Next slide, please. There we go. So the next slide just sort of puts all the different generating technologies in perspective. You can see, so the higher up on the chart it is, the greener it is, or the cleaner it is, and the farther to the right it is, the lower the CO2 emissions and the higher the efficiency. So you can see the fuel cells basically at a size of, a megawatt to 50 megawatts are as good as, if not better than, the large combined cycle power plants, which are the workhorse on our grid today. So it's a real paradigm shift. It allows us to put the best and the cleanest at a small size at a local inner city location, which is not something that previously has been available to people. Next slide, please. So here's just sort of a comparison to see where they're at. You can see sort of, as you go across that, I'm not going to go through all the different boxes, but it's sort of your consumer reports chart that shows how fuel cell stacks up to wind and solar and conventional generation. And the big thing that you see from that is where solar is maybe 15 to 25% capacity factor. That is, you get electricity out of it 15 to 25% of the time. And wind is 20 to 35% capacity factor, so you get electricity out of it 20 to 35% of the time. Fuel cells are there all the time. They have as good an uptime as a conventional combustion power plant, in terms of capacity factor, but they don't have any of the negatives in terms of siting or pollution or regulatory issues associated with putting them in. So that makes them a very good selection for putting in if you're in a location where you can do distributed generation or need intercity power support. Next slide, please. So I've got 3 case studies I wanted to go through. The first one is a very interesting one. It's Connecticut, Central Connecticut State University. This particular one is a 1.4 megawatt power plant. It's integrated with some other distributed generation. An interesting story about this is it was going in long before we knew what Sandy was, and Connecticut was in the process of putting this in as part of its normal fuel cell CHP program. But the university was very forward-sighted. They decided that they had wanted to put this in, use it with their generators, so that the utility could be powered up in the case the grid wasn't available. And that happened during a time period before the first of a series of storms. Before Sandy, 2 years earlier, Connecticut was in the unenviable position of having 2 storms. One went through in the summer and one went through in October that took the power out basically for the whole state for 7 to 10 days. And it was unheard of to have those kind of power outages for that duration in that area prior to that, but we went through that. This project was in construction at that time. It actually was about to be started just as the second storm went through and came online slightly after the second storm, so it wasn't available to support the university when the storms went through and caused it to shut down, but it was as soon as that storm was over. What that did is that the state realized that having something like a university available and running when the utility grid was down for an extended period of time, like a week to 10 days, had a lot of benefits. We were very fortunate in the second storm in that it was 70 degrees after we got 30 inches of snow the next day. Because had it been cold, there would have been issues with where do you put people with the power out and cold and freezing and all that sort of stuff. And a university that's got a gymnasium where people can stay, dormitories, kitchen that can cook food, and a library with internet access so people could do their banking would be a good resource to keep up. And that's sort of where the current vision of a microgrid started to come together. We call it reliable power, microgrid, many different things. They've been around for a long time, but we've realized now that people are so dependent on some of these services that we take for granted that being without them for a week to 10 days is something that we don't want to do. This is a really good example of how that can help, and it was very early in the process at a university, which is a good site for that. This particular plant generates a lot of the electricity, and it allows it coordinates very well with the existing diesel generators, other generation that's on the site, so when the grid's not there, the university can run just as a business-as-usual case where they don't have to shut down any of their services or anything, and they can be an asset to the community. So that's what, in that time frame, that if you come forward 2 years with Sandy, is really what has re-energized this thought about microgrids, critical infrastructure support, and how that can become a part of our grid for today. Next slide, please. So here's another one. This is a hospital. You can imagine the kind of places that you wouldn't want to be at and when the grid goes out for any extended period of time. One of those would be a hospital. How does a hospital stay up and keep running? So this is actually a very interesting project. It's what we would consider a microgrid today. It came on before Connecticut's microgrid program was implemented, so it didn't have the benefits of doing that, but the folks that operate this hospital were looking forward enough to see what the benefits of this were, and basically put together what we would call a very good example of a critical infrastructure support microgrid today. So the fuel cell is there. It's a 1.4 megawatt fuel cell. It runs 100% of the time, supplies baseload power, consumes natural gas to do that, so that the gas supply isn't dependent on diesel trucks showing up with diesel fuel in the event of an outage, which, as we saw during Sandy and these other events, the logistics of which can be very difficult to keep up and running for extended periods of time. So every kilowatt hour that it generates is diesel fuel is not needed for the diesel generators on the site. There's also a small combustion turbine on site, which is generating power between the fuel cell, the combustion turbine, the diesel generators, and some solar. They basically can maintain 100% hospital activity in the event that the grid isn't there and seamlessly transfer from one to the other. So what is the advantage of that? You've got the fuel cell, which is on as a CHP attribute all the time. So even when the grid is there, which is almost all the time, the unit is in generating power, saving the customer money relative to buying power from the grid. It also generates steam with the waste heat from the fuel cell. So besides the electricity provided for the fuel cell, it's generating steam for the hospital, which it uses in its energy system for heating and cooling and other processes that are used in the hospital. And at the same time that it's doing that, it's got the lowest emissions profile and a very, very low carbon footprint, which helps reduce that carbon footprint and the emissions output for the hospital on a day-by-day basis, even while the grid is there. So it's a CHP operating unit when the grid is there, and it's a microgrid should the grid not be there, and can continue operating when the grid's not present to keep the hospital fully up and running. That's a very good example for critical infrastructure support, which could be that university, if it's a emergency preparedness center, or other types of facilities like that that are operating in a grid support mode for when the grid isn't available. Next slide, please. So on the next slide, this is an example on a larger scale of how this can be. This is a utility scale application. This is a 15 megawatt plant in Bridgeport, Connecticut. Okay, and it's if you go through that, you can see it basically went in a period of a year, which for a 15 megawatt plant is very good. That includes all the permitting and things required for it. Didn't require emissions permit. All the siting consultations and everything basically turnkey in a year. That's a good. It's supplies power to the utility side of a substation for Bridgeport, by the port of Bridgeport. It also has 2 other substations that it's supplying. So this plant basically is feeding 3 different substations in inner city Bridgeport, which is the largest city in the state of Connecticut. The heat in this particular plant, because it's a large plant and doesn't have a industrial host on site, is being used through something called an ORC, an organic bottoming cycle, which is generating additional electricity. So that raises the electrical efficiency by turning some of that heat that's available into additional electricity without any additional fuel requirements. It's supplying power in that dense urban I-95 corridor area right near the port in downtown Bridgeport. It's right along the Metro North train tracks. You can see it if you're ever traveling through that area, right alongside the edge of the road there. And it's on about a 1.5 acre brownfield site. So if we think of that, to put it a little bit in perspective, it's a 15 megawatt generating plant, which if we were to compare that to one of the other non-polluting plants, like, say, a solar plant, you would be looking at something that's on much more on the order of, say, 7 to 10 acres in size, not 1.5 acre in size. And that generating plant would only be available in Connecticut probably 13 to 15% of the time. So instead of generating power all the time like this plant does, it would be at about 13 to 15% capacity factor on that site. So you can see you're getting a lot more kilowatt hours in a very urban constrained area with this fuel cell without any of the emissions issues associated with traditional kind of combustion plants. So this particular plant could keep 3 of those different substations, parts of those substations up in the event the grid's not there. And when it is there, it prevents transmission importing requirements on that particular substation in this area in southwest Connecticut, which is a grid-constrained area where the transmission lines are having difficulty bringing that amount of electricity into the system. So those are 3 different cases where you can see at a university, a hospital, and here at a utility substation area where fuel cells can provide power into the grid when the grid is available and provide power for customers when the grid's not available. Next slide, please. So just as sort of a recap on that, the advantages for a fuel cell CHP plant, whether it's the smaller behind-the-meter type distributed generation plant or a utility scale plant at a substation or someplace like that. It's clean baseload power. It very well supports the microgrid or critical infrastructure support needs like we're talking about today. It's got a very high electrical efficiency and a competitive energy cost, near zero emissions without any noise issues to worry about, and it's very easy to site and permit. And for that attribute, you're also able to get high-quality waste heat for cogeneration, which can easily be turned into steam, hot water, or absorption chilling so that you can do cooling as well. Next slide, please. So thank you very much for your time this afternoon. I look forward to your questions.
Thank you, Andy, for that great presentation. We've got lots of questions already rolling in. So just a reminder for folks throughout the presentations, you can use the question and dialogue box to type in questions, and we will do Q&A at the end of the 3 presentations. Our next presenter is George Bernstein. He is also from Fuel Cell Energy, which he joined in 2000. He's the Director of Electrical and Controls Engineering and leads a team in new system development, applications, and field performance improvement. His areas of responsibility include power conversion, electrical subsystems, and utility grid interconnection, as well as automation software development and instrument and controls engineering. He has a BS in Instrumentation and Electronics Technology from the University of the State of New York and is a graduate of the U.S. Navy Nuclear Propulsion Program. Thanks for joining us, George.
You're welcome. Good afternoon, everyone. My talk is really trying to give the utility perspective to fuel cell distributed generation. As in my introduction, that's an area of my responsibility. So we've worked with a lot of utilities, putting in a lot of different fuel cell applications. So we deal with this, day in and day out. So I'd like to talk about the status of electrical interconnection, the benefits of distributed generation for the electric grid, and trends. What's happening now and what's on the horizon for the future. If you ever do one of these interconnection with the utility, they usually give you they remind you that the entire grid was designed with one-way power flow. So, just looking back at the 20th century grid, it was conceived with large central power plants, sending power over transmission lines at high voltage, and then stepping down the substations and servicing loads. So the power always went in one direction, which, that simplified the electrical distribution. So things have, this obviously was a great achievement in the country, very smart people, but it was very limited in the sense that, this paradigm of central power plants. So what's happening today is we have this increasing penetration of distributed generation, and I won't go into all the benefits of distributed generation, but just at a high level, it promotes sustainability because it allows all these new clean and renewable resources to really provide power into our system. It improves energy efficiency. Even security is enhanced with distributed generation. So that's one of the drivers of why there's an increasing amount of distributed generation. It has the benefit of lessening transmission system and substation loads and losses. Now, one of the challenges, especially with intermittent distributed generation such as solar and wind, when these interconnections come through, the utility has to assume the worst case of minimum and maximum output. As Andy was talking about, what we're referring to there is capacity factor. So if you were to put in, say you wanted to interconnect a 1 megawatt PV system, over the course of a year it would only be putting out an average of 200 kilowatts. But as far as the utility is concerned, they have to design everything to the 1 megawatt level, even though they're only getting a quarter of that energy over the year. And so that ends up limiting the hosting capacity of the system. You're kind of tying up some of that capability of the system for the nameplate of that power plant. The other thing that becomes an issue is power load or the generation load balance. That always has to be maintained throughout the bulk electric system, and they have to be prepared to deal with cloudy days or wind dropping off immediately, and they have predictive models to address that. But it is a complication, and as you get more and more distributed generation, it becomes more and more of a technical challenge. So looking at fuel cells as distributed generations, we have this very high capacity factor that's similar to our baseload nuclear units and gas turbine coal units on the central power plants, with all the benefits Andy talked about, obviously. And so that facilitates that grid generation load balance because we're constant power output. And it allows the utility to make plans around that benefit of lessening loads on the system. They really can't take credit for that if it's not a firm power or baseload power. So it allows for maybe deferring a substation upgrade, or perhaps in larger amounts it could defer transmission system upgrades, which are very difficult to implement. And just an example of where things are and a trend we're seeing is the Connecticut Renewable Connections program. And it's a pilot program in Connecticut that allows our two major utilities to procure 10 megawatts of renewable distributed generation. So, our utilities were deregulated years ago. They had to sell off their generation assets, but in view of distributed generation's benefits, it's been recognized that distributed generation could actually improve the distribution system. So there's benefits for the utility in terms of planning and system load relief and improving power quality in their system if they could own these assets themselves. So Connecticut has this pilot program to put in distributed generation, and then hopefully there's a follow-on program that would allow them to site more generation in the distribution system. And this promotes a collaborative relationship between utilities and DG providers, and it really maximizes the potential benefits of distributed generation, because when we do projects, we don't know where the utility is going to be most benefited from it. It depends on our customers, where that goes in. But if the utility owns these assets, they can put them in key places to relieve a load congestion. And where that program's at, 7.8 megawatts of fuel cells have been selected by United Illuminating. Our first unit is just started up in the last week or two in New Haven. We have another one at Bridgeport Seaside Park, which is a 2.8 megawatt plant that's under construction. Should be starting up in August. And then in Woodbridge, we have a contract pending for another fuel cell generator under this program that the utility will own these assets. And I wanted to talk a little bit about trends in interconnection. There's a lot of changes coming along in terms of interconnecting distributed generation to it. And basically where the utilities are addressing increasing levels of distributed generation penetration in their system. So it's a big change in philosophy. Originally, it was the codes, basically, the philosophy behind our grid interconnect codes say that if the grid goes abnormal, that the distributed generators should get off, and they should stay off until the utility system gets everything stable again, and then we're allowed to reconnect and start generating into the system. And the other aspect of today's philosophy is thou shalt not regulate voltage. They don't want us regulating voltage. They have schemes to regulate voltage, of course, and they don't want any distributed generation interfering with that, so we don't regulate voltage. We just follow it when we produce power. But however, with increasing levels of DG penetration, that philosophy is changing. The new philosophy is that if the grid goes abnormal, voltage or frequency excursions, they want us to stay connected and help stabilize the grid. And we refer to that as ride-through. So instead of getting off and letting them try to stabilize it, they want our help in stabilizing it. And again, this is really key for high levels of distributed generation penetration. In California, they have so much distributed generation that in aggregate, if they will all take themselves offline on some bulk system transient, it would be the equivalent of losing 1 or 2 nuclear units, which would just make whatever problem started a sequence even worse. So they want, with new generation starting in 2016, they want the distributed generators to stay connected and help recover the system. So we'll just keep feeding power into it. And they also want us now to be able to regulate voltage. They want to have us with capability that they can select different modes of voltage regulation. They would tell us how they want us to operate and help them improve the power quality of the system. And that actually will improve the hosting capacity of the system. It will allow more distributed generation to be connected with these new features. So where this trend is at is in Europe, these are the requirements today, these new requirements. Denmark and Germany in particular have very high penetrations, upwards. Well, Denmark, I think the other day they were 100% wind for some time. In New England, we're about 6% renewable, so we don't have that level of penetration yet, but we're growing there. California is ahead of New England in a very large amount of solar PV. So they are implementing these requirements, as I said, in the latter half of 2016. And the national standard for the U.S., IEEE 1547, is presently undergoing revision to address these same things. That will take another couple years before the national standard is changed. And that was the end of my presentation.
Great. Thank you, George. Keep those questions coming. And moving right along to our next presenter, our next guest speaker is Bud DeFlaviis. He is Director of Government Affairs for Fuel Cell Hydrogen Energy Association. It is the premier trade organization for fuel cell technologies. His primary task there is to support the organization's mission to promote fuel cell and hydrogen technologies with federal, state, and local policy makers. He was an account manager and communications director for the Keeling Group before joining FCAT. He began working in Washington in 2001 as a press secretary for a senior member of Congress, and he earned his Bachelor of Arts degree in economics with a minor in political science from Penn State University. Thank you for joining us, Bud.
Well, thank you. I appreciate the opportunity and the venue. You've heard from some interesting folks. Andy and George gave really good presentations, so I'm going to turn your attention to kind of the boring stuff, the public policy discussion. And before I start that, I will, let me see if I have control of this. There we go, about FCAT. I'll give you a little background on where our organization, as was mentioned, we are the trade association here. for the fuel cell and hydrogen industries, and that is a pretty diverse group of technologies. As was mentioned, and I just think it's worth underscoring, fuel cells have some great potential to deliver clean, resilient, reliable energy across a variety of sectors. And as you'll see in this next slide, we represent kind of the full global supply chain. As you can see, we do represent fuel cell energy and some of the stationary manufacturers. We also represent, and some of you may have heard, a lot of buzz around vehicles. We also represent major automobile manufacturers and industrial gas companies that are in the market to develop and deploy fuel cell electric vehicles. But this is more, again, on the stationary side, and I'll focus at least the policy discussions around those. There are some very well-known companies and also some small startup companies, household names, not so familiar companies, really showing you the breadth and diversity of our membership and this industry that's taking shape. As we mentioned, I do lead we have a variety of committees. I help lead the Government Affairs Committee, along with all our private sector members who are interested in this kind of outreach. And our mission is probably pretty self-evident, but not surprisingly, we work on education and advocacy and good policy for fuel cells. There are some interesting things out there, some good policies, and some things that we'd like to see changed, and I'll kind of get into that in a moment. But first, one thing that actually I wish I could take more responsibility for this, but my colleagues are largely responsible for the content, the content and the gathering of all this information on. We have, for state activities and state policies, we have two major documents that we publish, which one is the State of the States, Fuel Cells in America. This is, I mentioned the 2014 edition, but it's a yearly comprehensive report on activities throughout the states. The state policy report is a little more specific breakdown on legislation and getting really into the weeds on the incentives and how that looks. I will give a little commercial to our group in that we are coming up probably by the fall or winter. We'll have the 2015 versions of these two publications, and I think they are really great source documents, if I'd say so myself. So one thing, if you look at these documents, one thing I think becomes clear, and we even make mention of this in some of the newer version. We've kind of come up with some top states. There are some areas of the country that are really forward-thinking, that have put a lot of thought into this, that are really want to see fuel cells take off, and it's usually a combination of vehicle technology as well as the stationary. But again, on the stationary side, those are generally the same parts of the country, and there are some attributes that are similar across all those quote-unquote top states. Usually the economic and the state development agencies, the environmental agencies are all familiar with fuel cells. Lawmakers and governors are, again, familiar and want to do what they can to promote the technology. Researchers and businesses, obviously the collaboration between those are very important. And then there are some partnerships and coalitions that kind of fall in between that help coordinate these activities, and those are and of course you have willing customers. Some customers in some areas of the country are more willing to experiment or to be first adopters of advanced technologies. So those are some of the attributes that we've seen, and we've started to kind of catalog in our state reports. Now, this list is that I'll run through briefly. This is not an exhaustive list, and if your state is not on there, and there are some very good states, but there were a few things that we found kind of over the years and trends, and some of those states that are really committed, and some policies behind those that have been kind of leading models for maybe some other folks to at least consider or model themselves after for consideration. California has been as I think was mentioned earlier, has been somewhat of a leader in in policies, again, not only on the vehicle side, but also on the stationary side for fuel cells. There's one program in particular, SGIP, the Self-Generation Incentive Program, and it helps with the distributed energy systems. Usually it's on the customer side of the meter, and there are some financial incentives there that, and there, of course, there are certain caps. Again, there's up to, I believe, up to 3 megawatts, and there's an incentive cap there as far as the actual rebate for the installation. Connecticut also is a kind of a leader in leading state with regard to fuel cell policy. There's a LREC program, which is a long-term program designed to fund customer-side renewable generation projects. There's a ZREC and an LREC. The LREC is the one that really that the fuel cell companies are able to take advantage of, or at least use to site fuel cells. New York is also has been very active in fuel cells for a number of years. They have a program, sub-program managed by NYSERDA, which does a lot. It really has some creative and some long-lived efforts to experiment with and to help deploy advanced technologies that have some societal benefit. They have both a large and a small fuel cell program under their customer-sited tier program, and funding becomes available at various times on a first-come, first-served basis. New Jersey has also been very somewhat active in and has been interested, I'd say more so, with some of the storms, some of the challenges they've had with resiliency. The primary, initially the primary deployment of mechanism was the Clean Energy Fund, but there, as recently as 2014, there's been the creation of an Energy Resilience Bank, which could very well benefit fuel cells, again, to try to deploy more base load, reliable power, again, that is less dependent on infrastructure that can get knocked out, or in the case of an emergency. So all these states have some very beneficial policies. Again, I don't mean that's just a 30,000-foot view of those states. Areas of the country like Ohio, South Carolina, Pennsylvania, and a few others have also had some very notable policies and some attempts to try and proliferate the technology. And so, again, I didn't want that to be an exhaustive list, but that just gives you an example of a few areas of the country that are looking at taking a serious look at fuel cells for a variety of reasons. FCHEA, through our government affairs activities, we constantly comment, or we try and comment where our members ask us to on various state policies or the continuation of state policies. And just very briefly, there have been some recommendations, and we've made some public comments that are available for folks to look at. But there have always been kind of some proposed changes or decreases in funding or what have you that try to either change or modify programs that are working well. And of course, we make on behalf of our base, our member base, comments that serve to extend the life of policies that are beneficial, that again lead to more resilient infrastructure and lower pollution outputs, and a more resilient infrastructure for everybody. That's kind of a quick overview of some things happening in the states, and I will say what has taken most of our time really has to do with the federal side of the government ledger. Again, there are other programs within the government. There's appropriations that fund research and development and some other exciting areas. But as far as commercialization and getting products out in the marketplace, the real idea is, and the real helpful policy driver has been the investment tax credit. The investment tax credit's been around for a few years, since 2005, and the benefit, or the credit, is set up so that there's a qualifying fuel cell property is eligible for a 30% up to $3,000 kilowatt credit. This has been extended a number of times because of the way it was written. It was only offered for a few years here and there, and I would say that there was obviously it was instrumental in helping to get some early market traction, and will continue. So this is really, again, the key driver, I think, for a very important piece of legislation for our members. As I mentioned here, it's set to expire in 2016, and we're looking at ways to extend the life of that for a variety of reasons. But I wanted to talk briefly about some efforts that lawmakers at Capitol Hill have talked about, and many of you have seen a lot of buzz or have read about tax reform, and there's a growing effort to change a variety of tax credits. This doesn't have to do with energy policy, but we would be potentially impacted by any sort of major reform. Very briefly, there have been many efforts, and again, this growing consensus to try and change large portions of the tax code. In the beginning of the year and up until very recently, that was kind of the marching orders that many of the leaders, the tax writers on the Hill, were following, and there were some interesting comments and proposals and ideas out there to make a kind of a simpler, to steal a line from some lawmakers, a simpler, flatter, fairer tax code, and whether that impacted the energy credits, again, was kind of an idea up for discussion. In short, I think the idea of comprehensive tax reform is essentially dead this year, meaning I don't think you'll see some kind of sweeping changes like we saw in 1986 of the tax code that was really, really comprehensive in nature. But what does that mean? So where does that leave the industry? We've kind of looked at, we made certain comments, and we've worked with our friends on the Hill to talk about what reform would look like, but also we've had conversations with them saying that, look, reform is fine, and we welcome, the opportunity to weigh in on that, but there's the clock is ticking, as I said here in the slide, and we need to have a conversation to give to extend the tax credits that are working or are starting to have their desired impact, and extend them for a few more years to give industry a little more certainty, and people who are interested in developing alternative energy the confidence that they know that there will be certain assumptions that they've had made in their business planning that will continue. So this is not unlike, this is not a problem unlike unique to fuel cells, but we are caught up in this idea that we need some certainty. We need to know what the rules of the game are, and Congress appears to be actually next week will appear to start to tackle some of these tax extender credits for the federal incentive, and we're hoping they do that. So, we've been making the case for these credits in a variety of ways. Again, not only talking about the attributes of the technology and how far we've come, and frankly, some of the good news stories, but we've tried to answer for lawmakers a set of frequently asked questions, and we kind of compiled those, and some of that was covered, I think, by Andy and George, and they've touched upon some of these areas, but we've made efforts to talk about the current state of the stationary backup and fuel cell material handling market in the U.S. and while we are making a tremendous progress, we are still relatively small compared to some of the other technologies, and so concerns about cost and concerns about the availability of the credits to this industry are noteworthy, I think, to bring up to lawmakers, and we've done that. There is a sense of urgency, like I mentioned, and people have been confused by this. and we try to let them know that while they do, the credits for the federal incentives don't expire until 2016, the sense of urgency is this. There are, it takes some time to site these projects, and solar and wind have this, fall under the same categories as well. And really some additional consideration before they expire would really be helpful. The historical costs, as I mentioned, have not been terribly expensive to the government. So these incentives are very, very valuable to our industry, and they are not main drivers of debt deficit to the federal government. How does the ITC for fuel cells differ from other technologies? Andy's discussion on availability and the availability of fuel cells really is an interesting fact for a lot of lawmakers to understand, knowing that the capacity factor of fuel cells is much higher. This is the same credit that solar gets essentially, but we offer power for base, usually in base load situations, that makes the efficiency of the credit that much more appealing. So we've tried to get that message across. Again, this takes some constant education and advocacy from our part. One thing that actually is very interesting, and again, I think Andy's presentation talked about it a little bit as well. You can get a lot of power out of a fuel cell on a small area of land, and while that might not seem too important to folks out west, and maybe in the Midwest or some of the western states, it's very important to people in cities and in more congested areas. And so there are, in closing, I would say that the credit is not just for renewables, it's not just for wind and solar. There are a lot of considerations that lawmakers, I think, are starting to understand, that the certainty is very important to everybody. These are not just, again, these are technologies that are extremely clean and provide a slightly different complementary group of characteristics to fuel to some of the other traditional renewables. And so we have I think we have a strong case to make, and I think these incentives and others in the states, leveraged properly, will help us continue to grow, and again, to help us continue to make a grid that is much more resilient, that is much more prepared for the demands of the 21st century. So with that, I'll turn it over and answer any questions if needed. Thank you.
Great. Thanks to you, Bud, and thanks again to George and Andy. Those were a terrific trio of presentations. I feel as though we covered a wide breadth of information covering different fuel cell applications in different sectors, from the utility and grid stability to distributed use in microgrid situations or critical facilities. Also, a great wrap-up detailing the federal and state political landscape and the policies and programs currently supporting fuel cells. So I have a bunch of questions, and if you didn't have an opportunity to type one in, please feel free to do so now. We'll spend the next 10 minutes addressing the questions from the audience and dig a little deeper. It is interesting that, despite the great efficiency of these machines and the low emissions associated with fuel cells, that, as Bud pointed out, there isn't great uptake at this point compared to other renewable technologies for fuel cells. So let's talk about cost. We had several questions come in about the cost of these systems, and I don't know which one of you would like to answer these questions, but let me throw out a few, and George, Andy, and Bud, as you see fit, feel free to answer them. Let me direct this one at you first, Andy. Can you give us an idea of what it costs to build the 15-megawatt plant in Connecticut that you showed up on the screen, and also give us an idea of the footprint of that plant?
Okay, that's a good question. So the easiest way to do that is you look at it for the way that we buy electricity, which is cents per kilowatt hour. So that plant is actually making electricity for about 11 to 13 cents a kilowatt hour, depending upon cost of gas and all the other sorts of stuff. And that's sort of a data point that fits in with most of the other plants. So if you look at it over the long term, you can think of a fuel cell plant in the size range we're talking, say 1 to 40 megawatts or so, to be in the, say, 10 to 13 cents a kilowatt hour cost, depending on what the cost of gas is and the efficiency for tax credits and some of those types of things like that. Footprint, you can see the smaller, the 1.4, is about the size of a tennis court. That plant in Bridgeport is in a little bit over an acre. It's about less than an acre and a half, about I think it's 1.27, something like that, acres of land in an inner city.
Great. And excuse me, but I can't remember if you said there was CHP associated with that plant, and if there is or if there isn't, what would how would the cost change with or without CHP for that size of plant?
Well, that one is unique in that it has CHP, but it's using the heat to generate additional electricity. So the way that shows up is you pay additional for the electrical or for the installation up front, but then you make it back on buying less gas to generate electricity because the efficiency is higher. So it probably technically wouldn't be considered a CHP plant. It would be considered a combined cycle plant because it has two forms of generation. But in essence, it's taking the heat from the fuel cell to make additional electricity, which doesn't require any fuel, which is enhancing the economics.
Okay, thank you for that. Well, then let's talk about costs compared with other renewable technologies like solar and wind. Bud, would you be able to speak to that and perhaps also tell us what the market is like outside of Connecticut?
Well, the cost comparison between solar and wind, I wish I could.
Okay.
The short answer is no. You are seeing, I think, well, one thing that I think is unique, you are seeing obviously states with, well, you're seeing some really growth areas in states where there are a lot of data centers, and I think some people will automatically assume, and the costs I think are probably a little higher than traditional grid-generated electricity, but again, it all depends on what part of the country you're from and what the energy mixture is. So again, there's always that big. You mentioned that I was an econ major, and my first my first class in freshman year was always my economics professors would always say, well, it depends, and so there's always that it depends. But we are seeing some companies and some early adopters who are willing to pay the premium, not only the kind of a resiliency premium, but also an efficient or a reliability premium as well. For a data center to go down for maybe a Walmart that has a lot of frozen food, or if their power goes down for any given time, it can be extremely costly. So yes, there are obviously the states where there are a lot of incentives. That seems to be where the technology tends to flow more easily. But data centers and other critical infrastructure in all 50 states, and there are a few examples, some notable examples of companies that are, again, were willing to pay an additional premium. I've seen various estimates of the cost of wind and solar, and I can say that there are there's some interesting conversations with that as they relate to the how much longer certain incentives should be continued, but those are political discussions, frankly. But again, I would say that for fuel cells, we haven't had a kind of a bite at the apple for very long. Our costs are coming down. We do provide something that the other technologies don't provide, which is, again, and this is for baseload power, there are stationary fuel cells that provide backup power as well, so I don't want to leave them off the table. But for the baseload power, again, we have a high capacity factor and reliability that is really, I think, unmatched. And you're starting to see, again, some people that are willing to pay a little extra knowing that their electricity demands will be met regardless of, again, weather conditions or time of day or the health of the grid.
So Val, if I may, maybe I can add just
Please.
a little bit to that. The way we tend to look at it is the wind, large-scale wind, is probably 7 to 9 cents, but that's not in Bridgeport, Connecticut. That's in the Midwest somewhere. So when you add the transmission cost to get it into that area, it's probably about the same competitive-wise. I think the wholesale power cost in Bridgeport is probably around 8 to 9 cents today. It's about there, so that's about the same sort of cost as you would get for wind out in the Midwest. But then you've got the transmission issue. Large-scale solar probably is about the same price as the Bridgeport plant in terms of cents per kilowatt hour for electricity. But again, you couldn't put it in downtown Bridgeport. You'd have to put it in a large area, and it's much better suited for the south than it is. The farther north you go, the worse the capacity factors of those plants become. And then if you look at the small solar on rooftops and stuff, they're significantly more expensive than the large fuel cell plants.
Great, thanks for that additional information. We have surpassed the hour, but we still have a bunch of folks still attending the webinar presentation. So if folks don't mind, we have lots of great questions if we run over a little bit. And of course, if you need to leave, this webinar is being recorded. You can always check back on our website and download the audio. You talked about high capacity figures and high efficiency. What about operation and maintenance costs and the durability of these systems? What else do fuel cells have going for them?
This is Andy. I'll take that one. I would say those numbers that we've been using are all-in costs, including all the maintenance requirements and all the long-term and short-term maintenance costs, operating costs, and everything in them. Breaking out the individual pieces isn't really good because it really is what matters is the end number of cents per kilowatt hour. How much of it is, wiping solar panels clean so that they do that versus saving up money so you can replace a fuel cell stack every 5 to 10 years like is required. It doesn't really affect the economics very much. It really is the end economic cents per kilowatt hour that are important.
Okay, good to know that that's already been calculated. Now, is that true for the distributed systems, and what are the costs there?
Yes. The only numbers we look at are sort of full-in loaded costs for that because if you don't include those numbers, then someone tries to put those in their pro forma to run the numbers on what their economics are going to look like, and they end up with a very bad surprise when they start the plant, and you end up with a dissatisfied customer. So that business model doesn't work very well. You really need to have all the costs in so that you're comparing apples to apples when you're comparing it versus all the other different technologies.
All right. Terrific. And this is for all of you. Do you have a sense of how many utilities are using fuel cells currently and how they are being used? Are they generally in areas where there are high levels of distributed generation penetration, and are they providing stability? What's your sense?
This is Andy again. I can take a crack at that. I don't know the actual numbers of that. I mean, numbers are increasing, and they're increasing rapidly every year as we're starting to get traction. It's not just us. It's the other fuel cell companies as well. But generally, the fuel cells are sort of in California and maybe that part of the Pacific Northwest there and sort of the Boston to D.C. corridor, that area. It's the populated areas. And what it comes down to is it's the people that place an extra value on extra clean emissions because of pollutant constraints for meeting EPA requirements and things like that. So it pretty much is the West Coast and the Northeast corridor down to Washington.
Great. Does anyone have anything else to add to that?
I don't, but that's my understanding as well, yeah. I think Andy's spot on with that.
Great. We have had a few questions on emissions and efficiency, and quickly, could you sum up the efficiency of a fuel cell versus a backup diesel generator?
We can do that. It's on that chart on my slides, actually, if you look there, I think. But, I mean, depending on the application, I mean, our fuel cells run from 47 to 70% in electrical efficiency. Typical diesel is probably 30%. And then there's the heat component if you use the heat. If you use the fuel cell, you can get up to 90%, and similar for the diesel, the difference being that the fuel cell would allow, our fuel cell at least, would allow you to generate steam, which is a higher grade heat, which is more valuable for some of the heat versus just hot water for domestic hot water or district heating or something like that, which would be the diesel.
Okay. And a few questions about fuel source. Are the majority of the fuel cells being fueled by natural gas, or is there a percentage that's being fueled by hydrogen?
They're not. This is Andy again. The hydrogen's not very available, so the fuel cells fueled by hydrogen tend to be really small. They tend to be things like UPS backup supply type things where you can put the hydrogen in a bottle to fuel them. Fuel cells generally use natural gas because that's what's available. A significant amount of our fuels actually are fueled by biogas from an anaerobic digester plant, things like wastewater treatment plants or breweries, or we've got an onion manufacturer that uses the waste from that to generate biogas to fuel the fuel cell. So the fuel cells can use quite a variety of fuel, but the reality is that natural gas, methane, is what's typically available and what most of them are run off of.
And does efficiency change based on the fuel source, let's say natural gas versus biogas?
That's actually a very interesting question. The engineer in me would say no. The scientists, actually, the units running on the biogas are actually a little bit more electrically efficient. It's really mostly a negligible amount.
Great. I think that pretty much wraps up all the questions in the various categories: cost, emissions, technology comparisons. Unless anyone has, any of the three of you have anything to add, I think we can wrap up.
No, I think I'd just like to thank everyone for their time and Val for setting this all up and allowing us this opportunity to talk to everyone.
It's our pleasure. Thank you for presenting. Thanks to all of you for listening. Thanks, Sam, for setting this up. Have a great day, everyone.
Thanks, everyone.
Thank you.